So today what we're going to talk about is the how to evaluate limits when problems happen, okay? So yesterday was we just be able to plug them in and calculate and figure out what the limit was, right? So here we go on this on some reviewing of some factoring rules that you really need to know, okay? So a squared minus b squared, that's a difference of squares, okay? So this factors into a minus b times a plus b, okay? A cubed minus b cubed, that's a difference of cubes. And what we need to really remember is that the first factor is always the a term minus b. It's what you're cubing minus what you're cubing here, times, and then a squared plus ab plus b squared. And I showed you guys this last year, okay? And a cubed plus b cubed is very similar to this one, okay? But instead of a minus b, this first factor is a plus b. Now, it's really important that you know this first factor. I can get this other one for you and show you another way to do it, but you got to know this first factor, okay? So a cubed plus b cubed, the first factor is a plus b. The second factor would be a squared minus ab plus b squared, okay? Now, these next two right here, I want to show you, they could be written as a difference of squares, okay? Now, how can that be a difference of squares? Well, if you take a squared and square it, that would be a difference, that would be a perfect square, okay? And then minus b squared squared. Okay, so here's your squared, so it'd be this factor minus this factor. So it'd be a squared minus b squared times a squared plus b squared. And then a squared minus b squared, this is a difference of squares, so this one could be factored even further. Now this one couldn't, but this one can, okay? So this factors into a minus b times a plus b times, and then a squared plus b squared, and that one's not factorable. Okay, so a to the 6th minus b to the 6th, that could be written as a difference of squares, okay? How could that be? Well, you could take a cubed and you could square it, because that would be a to the 6th, and then minus b cubed squared, that would be b to the 6th, okay? So this is the difference of squares, and the two things that we're squaring are a cubed and b cubed, so this would factor into a cubed minus b cubed, okay, times a cubed plus b cubed, okay? And then this one, you notice this is the difference of cubes. So you could factor this one into a minus b times, and then a squared plus ab plus b squared, and then times this a cubed, and I'm sorry, this one is a sum of cubes, so that could be factored even more, and it'd be a plus b. I almost didn't do that one. I almost didn't see it, okay? A plus b times, and then this, and I'm going to put a little arrow here to show you, this would be a squared minus ab plus b squared, and that should be in parentheses right there. Okay, I ran out of room. Sorry. Okay. All right, so let's take a look at this first example, and I'm going to show you a couple ways of looking at this and doing it. So on this one, I want to show you where the problem occurs, okay? So let's try to do direct substitution, all right? So we try to do direct substitution, and we put in the 1, right? So that'd be 1 cubed minus 1 over 1 minus 1, right? That's that 1 for the x right there. Well, what's 1 cubed? Well, it's 1, right? Minus 1, so the numerator is 0, right? And 1 minus 1, that would be 0, okay? From here on out, this is going to happen a lot, okay? This is 0 over 0. Now, if you recall from last year, okay, when did that happen? And it's when we had rational functions, okay? And this causes not a vertical asymptote when you have 0 over 0, it actually causes a hole to happen. So this graph has a hole at x equals 1, okay? So how do we figure out the limit if we can't actually do a direct substitution like I just tried to do? Well, here's one of the options, okay? So option 1 is to factor and cancel. So this particular problem has 2 different ways you could do it. Okay, so if we want to, and you need to write this, okay? The limit as x approaches 1 of x cubed minus 1 over x minus 1, okay? What is this equivalent to? Well, this numerator factors because we should recognize this is a difference of cubes. So this is the limit as x approaches 1 of, and so this first factor, and that's the one you have to remember, is x minus 1 times, and then it's this first factor, which is x squared, so that'd be x squared, plus x times 1, which would be 1x, or just x, plus this 1 squared, right? Because that's your b squared, all over x minus 1. Well, x minus 1 over x minus 1, x minus 1 times this over x minus 1, that creates the 1, right? And so we can cancel. Now, you haven't heard this in a while, but it's, remember that? Okay, so we can cancel, all right? So what we're left with is this. This becomes the limit as x approaches 1 of x squared plus x plus 1. And we weren't able to do a direct substitution in this one, right? Because we had 0 over 0, okay? That's going to happen all the time in calculus, okay? But this one we can, and they're equivalent. So we can use this one right here to figure out what this limit is, okay? So this becomes, all we have to do is plug 1 in. So that'd be 1 squared plus the 1 plus another 1. Well, the 1 squared is 1, plus another 1 is 2, plus this one is 3, right? So the answer to this is 3, okay? So option 2, because the numerator is a larger power than the denominator, we could actually do long division on this, okay? So option 2 is to do long division. And we can do that as long as the numerator has a higher power than the denominator, okay? All right, so if we want to take the limit as x approaches 1 of x cubed minus 1 all over x minus 1, okay, we know from doing long division last year, okay, we know one of these factors, right? Okay, so we know one side of the rectangle. We know one of the factors is x minus 1, okay? So we have x minus 1 okay, and we have a 1 by 2 here. This has to be this x cubed, so x cubed. And then here we go with the long division. X times what gives you x cubed? Well, it'd be x squared. X squared times -1 is -1 x squared. Notice that we don't have any x squared. This is the, oh, I should say this. This is the area right here, and this is one of the sides. And what we're trying to find is the remaining side. I should have said that. And you know what? I just realized I need to slide this up just a little bit for you guys. Okay. So if the area doesn't have any x squareds, then that means when I add the next column, that means I have to have 0x squared right here, right? So if this is -1x squared, this would have to be +1x squared. And then x times what gives you +1x squared? Well, it'd be +1x or plus x. And x times -1 is -1x. And if you look, we don't have any x terms, right? So that means on this next column, this diagonal has to add up to be 0x because we don't have any x's, so that means there's 0 x's. So if this is -1x, this would have to be +1x. And then x times what gives you 1x, and it'd be +1. And 1 times -1 is -1. And there's what the division answer is. It's this right here. It's x squared plus x plus 1. Okay, so that means when you take the area and divide by this one side, this is the remaining side. which means I can replace this just like I did up here. And notice it's the same thing, right? And it should be. This is just two ways of doing the same problem. So this becomes the limit as x approaches 1 of simply x squared plus x plus 1. Because this area divided by this side gives you this side. And so it'd be x squared plus x plus 1. And so we can do it now. We can do the direct substitution, and then that would be 1 squared again, right? Plus the 1 plus 1, and that would again give you 3. So this limit, okay, even though we started out with a problem with having 0 over 0, okay, we got 3. So this is a technique you can do, okay? A technique is you can cancel or factor and then cancel like factors, okay? So that's one of the techniques. There's going to be several techniques we do here, okay? So for this next problem, we have the limit as x approaches 0 of the square root of x plus 1 minus 1 over x, okay? So let's try to do direct substitution, okay? So we try to do a direct substitution, and if we put 0 in for x, this first one would be 0 plus 1, which would be 1. That'd be the square root of 1 minus the 1 on the outside all over 0, right? And what's the square root of 1? Well, it's 1. So this would be 1 minus 1. So once again, we get 0 over 0, okay? So we've got a problem. This can't happen, all right? And I should say, I should have told you this a while back. I'm going to tell you, calculus is really easy. What's hard in calculus is all the algebra you have to know, okay? So this is an algebraic technique that we can use to figure this limit out, okay? So here we go. We're going to write this limit. You should write this and tell me what this is equivalent to, okay? So we have the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. Okay, so that's the original problem, right? And so now what we're going to do is we're going to take that problem, the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. Now, what we can do to change this is multiply by a version of 1, okay? Now, since this deals with square roots and it's a sum or difference here, we're going to multiply by the conjugate of this, okay? Because I know if I multiply by the conjugate from last year, okay, that if I multiply by the conjugate, I'm going to get rid of all my square roots because the square root is going to have problems here, okay? That's what's causing part of the problem, okay? So what I'm going to multiply by is this top is the conjugate of this, which would be the square root of x plus 1. And remember, conjugates are the same thing, but the middle term right here, not term, can't think what it's called right now. The subtraction should be addition, okay? So we have square root of x plus 1 plus 1, okay? So these two are the same, and in between, I don't want to say sign because it's not really a sign, the operation changes. This one's minus, this one has to be plus. Now, here's a problem. This isn't 1 yet. How do we make this 1? And to make this be 1, we are going to multiply by the same thing in the denominator. So square root of x plus 1 plus 1. Okay, so this is two terms, a difference of two terms, right? And this is a sum of two terms. We can use an area model to multiply this out, okay? So I'm going to do that right here off to the side. I'm going to make it a little bit long because it's square roots. Hopefully some of this stuff is coming back to you. Okay, so I'm going to take the square root of x minus 1. I said square root of x. Square root of x plus 1 minus 1, and then times it by this. The square root of x plus 1 plus 1. Okay? So square root of x plus 1 times the square root of x plus 1, well, that'd be the square root of x plus 1 squared, which would just cancel out the square root, and you'd be left with x plus 1. This one, when we take the square root of x plus 1 times negative 1, that'd be negative square root of x plus 1. When you multiply these two together, you get positive square root of x plus 1. And then positive 1 times negative 1 is negative 1. Okay, so we're multiplying by 1 here. That's a big idea. Okay, we're multiplying by 1, which isn't going to change what this value is, but it's going to change the way it looks. So then this is equal to the limit as x approaches 0. And what we have is x plus 1, right, minus the 1. Over, okay, so now this is a sum of two terms, and this is being multiplied by x. So we need to show this. I don't want you to actually multiply it out because you actually can't, okay? I actually want you should write x times the square root of x plus 1, okay? So if we try to do direct substitution, even right now, okay, we would get 0 plus 1 minus 1. This top would still be 0. This bottom would still be 0. So we still have problems, okay? But we can clean this up a little bit because this numerator becomes x plus 1 minus 1, or just x. So the limit as x approaches 0 of x over x times the square root of x plus 1, okay? So looking at this right now, okay, right here we have a common factor now. You see, this created it. This is what's causing us to have the 0 over 0. Because if we tried to do a direct substitution right now, we have 0 on the top and we're multiplying by 0 on the bottom. That's what's causing it. Now, because we have like factors now, we've rewritten this so these factors are the same. We can cancel these, all right? And what we wind up getting is the limit as x approaches 0 of 1 over the square root of x plus 1. All right, so now we put this 0 in. Can we do a direct substitution now? Okay, and the answer is yes. If I put 0 in here, this is going to be the square root of 1. So this would be 1 over the square root of 1 plus 1. As soon as you do the direct substitution, you no longer need to write the limit, okay? So that's why right here the limit isn't there, because I'm doing a direct substitution. Same thing up here. I did a direct substitution and realized that there's a problem, okay? All right, so what's the square root of 1? Well, it's 1, right? So this would be 1 plus 1 on the bottom, which is 2. So this is 1/2. And that's what this limit is. It's 1/2. If you were to build a table, you would get closer and closer to 0.5 is what the table would show, okay? So what this is called, this technique right here is called rationalizing the numerator. We usually do rationalizing the denominator. That's what I taught you last year. Okay, so there's a lot of stuff I showed you last year because I knew you were going to need it for calculus. This is one of them, okay? All right, so when would you want to do this, okay? It's when you have a square root and you have a sum or a difference, okay? So right here, let's say we had, well, if this had been plus 1, you wouldn't have gotten 0 over 0. But let's say for some reason that would happen, okay? So then this would have to be the opposite of this one. So if this one's minus, this one's plus. If this one's plus, this one needs to be minus, and the numerator and denominator would have to be this, would have to match for it to be a 1 right here, okay? A lot of big ideas, okay? A lot of big ideas. Okay, so let's go to the next example. Okay, so for this problem right here, let's try to do direct substitution, okay? If we try to do direct substitution and put 0 in for x, this first one would be it becomes 1/4 minus 1/4 over, and we put 0 right here for the x, right? And so 1/4 minus 1/4, look what happens. We get 0 over 0. So that's a problem, right? That's going to be that's a hole, okay? It's going to be a hole. All right, so how do we fix this one algebraically? Okay, well, what we have to do is you have to realize, oh, we have a complex fraction here. Taught you this last year too, right? Okay, so we're going to write this, the limit as x approaches 0 of 1 over x plus 4 minus 1/4 all over x, okay? That's going to be equivalent to the same thing, and then we're going to modify it. We're going to do something to it. Okay, so what do we want to do? Well, what's causing this to be a complex fraction is this denominator of 4 and this denominator of x plus 4. Okay, so what I can do is I can multiply by 4 and also x plus 4. And again, it's the same idea as above. Okay, I can do that as long as this is actually 1, right? So this is going to be 4 times x plus 4. Remember, this whole thing right here is actually 1, but it's going to get rid of the complex fractions, okay? So I really would love it if you could do this in your head, okay? And be careful because you have a subtraction here, okay? All right, so when we multiply this fraction times this, the x plus 4s are going to cancel, right? So this would be the limit as x approaches 0. My x plus 4s cancel, and I'd be left with 1 times 4, which is 4, minus. Okay, now, when I multiply the 4 times x plus 4 times the 1/4 here, the 4s are going to cancel, right? But I am multiplying by a sum here that's in parentheses, right? I need to keep that parentheses, okay? So parenthesis x plus 4. All over. Okay, so there's no denominator here, so it's just going to be 4 times x, or x times 4. I'm going to write it as 4x. 4x times x plus 4. We don't have that common factor yet, right? So what I can do now is distribute this negative. So this would be the limit as x approaches 0 of 4 minus x minus 4 over 4x times x plus 4. And then so right in the numerator here, we have 4 minus x minus 4. So we have 4, take away 4, right? We're just going to be left with this negative x or minus x, right? So this is equivalent to the limit as x approaches 0 of negative x over 4x times x plus 4. And so why are we getting the 0 over 0? It's really because this can be rewritten as an x over an x here, right? Now, what happens with these x's? They could cancel, right? Okay, so what are we left with? We're left with the limit as x approaches 0. Now, when we cancel these x's, what we're left in top is a negative 1. So negative 1 over the 4 times x plus 4. And now what happens if we do direct substitution? Well, we're no longer going to get the 0 over 0, right? If we put 0 in here, okay, this would be equal to negative 1 over, once again, I'm plugging the 0 in, so I'm not going to write the limit, okay? So, and I should, okay, I should be seeing this limit statement right here, right here, right here, right here. You can't, it means something totally different if you don't write it, okay? So you can't leave it off. Okay, so negative 1 over, and then this would be 4 times, and 0 plus 4 would be 4. So this denominator becomes 16. So our answer is negative 1/16. And that's what this limit is. Okay, so again, it's canceling out, right? So we're rewriting it. We're finding a way algebraically to rewrite it. Okay, we're going to do a thing called derivatives in calculus, and every derivative becomes 0 over 0. So we have to know these algebraic techniques really well, okay? So on this next problem, okay, what can we do? And we got to read this carefully, okay? This is saying h is getting closer to 0. This is not saying x is getting closer to 0. This is saying h is getting closer to 0. So in this expression right here, what we need to do the direct substitution with is h. So we're going to put 0 for h everywhere, okay? So here we go. So this is equal to, so this would become x plus 0 squared minus 2 times x plus 0 minus, and there's no h here, so it's just going to be x squared minus 2x all over. Okay, so here's my h, so I need to replace that with 0. Okay, and then what does this become? Well, this is x plus 0. That would just be x squared. So this would equal x squared. This is just x right here. And so negative 2 times x is minus 2x. And then minus x squared. And then plus 2x. All over 0. And look what happens. We have x squared minus x squared. Those are going to cancel. We have minus 2x and plus 2x. Those are going to cancel. So this is equal to 0 over 0. So we've got problems, right? Every one of these, we have problems, okay? So how do we fix this, okay? So what algebraic technique could you use to figure this out, okay? And this is what you would do, okay? What we can do is we can algebraically expand this out and see what happens, okay? So we'll start with this original problem. So the limit as x, not x, whoops. It's easy to do, okay? So just be careful. It's not x, right? It's h. The limit as h approaches 0 of x plus h squared minus 2 times x plus h minus, and then x squared minus 2x all over h. Okay, so what we could do is this is equivalent to the limit as h approaches 0. And the one thing we could do is multiply this out. We could square this, okay? Now, remember, I'm going to get upset with you if you try to write this as x squared plus h squared. It is not that. That is not a rule. You should not know that, okay? This is really x plus h times x plus h. If you need to, I'm okay with this. Do an area model. Do one side x plus h, the other side x plus h, and multiply it out and see what you get, okay? What you'd wind up getting is x squared plus 2hx plus h squared. That's what you would get if you multiplied one side of a area model, x plus h times x plus h. It's actually a perfect square, okay? And then if we distribute this negative 2, we'd have negative 2x minus 2h. And then if we distribute this negative, we'd have minus x squared plus 2x all over h. Okay, so what is this equal to? Okay, so if we look, okay, we have an x squared here and a minus x squared. Those are going to cancel. We have a 2hx. We don't have that anywhere else, right? So we have the limit as h approaches 0 of 2hx. Okay, so we have that one because that doesn't cancel anything. Plus this h squared, because we don't have that to cancel anywhere else. So plus h squared minus 2x, right? Minus 2x here. But then right here we have a plus 2x, so those are going to cancel, right? So we don't need to write that. And then we have minus 2h, and we don't have anything to cancel that, so minus 2h. And we already got rid of the x squared because it canceled with this one, and we got rid of this 2x because it canceled with this one. Okay, so then all over h. All right, all of these terms in the numerator have an h in common. So we could actually factor that out. So this is equivalent to the limit as h approaches 0 of h times, and because they all have h in common, we could factor out. So we have 2x plus h minus 2. That's just greatest common factor all over h. And that's why we have 0 over 0. It's because we have this h and this h, okay? So if we try to do direct substitution, this would be 0 and this would be 0, which causes the whole numerator to be 0. But what can we do here? We can cancel these, right? So we still haven't done the direct substitution. So we do the limit as h approaches 0 of, and these h's cancel, so we're left with 2x plus h minus 2. We can now do a direct substitution and put 0 in for this h right here. And what we would have is 2x, because that we're not putting 0 in for x because that's an h, right? Plus 0 minus 2. So that means this becomes 2x minus 2. And that's what the limit is. It's actually an expression, okay? This this is leading to something really, really big in calculus. You just don't know it yet, okay? So what techniques do we have? Well, you could factor and cancel like factors. We have rationalizing the denominator. If you come across a complex fraction, multiply to clear out the complex fraction, okay? If you don't have any of those, then and you have some squaring and stuff like right here, okay, then maybe you could, in multiplication, just go ahead and multiply it out and see what happens, okay? So those are techniques that you could see, okay? Techniques you could use, I should say. So these are some limits that you really, really need to know, okay? And here's the problem. Right now, we don't have a technique that could fix this, okay? All of these will come out to be 0 over 0, but we don't have anything that we can do algebraically yet to fix this, okay? So this is actually these two right here were ones I gave in an ed puzzle for you to do, okay? Just on Monday, okay? So this one right here we did earlier, okay? Actually, I think I did this as an example for you guys, okay? So this is sine x over x, okay? And I want to make something clear, okay? Because this is a trig function, it's not that it has to be x over x. It's just that this angle argument and this denominator have to match. And then same thing with this, okay? Because I'm going to go over this in just a minute. So the only way to figure this out is to build a table, because there's no way to algebraically figure this out with what you have been taught up to this point, okay? It actually is going to take calculus for us to figure this out, okay? So here we go, all right? So this is a limit this is a one-sided limit right here for this one, because for this to exist, right, the left and right hand limits have to exist. So this is 0.5, 0.1, 0.01. This is approaching 0, but from the right side of 0, okay? So this is the limit as x approaches 0 from the right. And what is it that we're approaching? Sine x over x. Okay, so what is, as x is approaching 0 from the right, what is the sine x over x getting closer and closer and closer to? Well, it's coming out to be 1, okay? And if you look at this is the same thing, but we're approaching 0 from the left of 0, right? Because all these x values are negative. So this one is the limit as x approaches 0 from the left of sine of x over x. And if we look at what's happening to that one's also getting closer and closer to the value of 1, okay? So what that means is whenever you see this, right, because the left hand and the right hand match, right, this limit exists and it's 1, okay? So anytime you see this, you know that's the equivalent of 1, okay? How about this one right here? And that's going to be this one, right? Okay, so this is the limit. This table right here, x is getting closer and closer to 0. So the limit as x gets closer to 0 from the right of 0 of 1 minus cosine x over x, okay? And what's this getting closer and closer and closer to is the number 0, okay? And let me slide this up a little bit. Okay, so this one is the limit as x approaches 0 from the left of 1 minus cosine of x. Let's make that look like an x. Over x, okay? Because we're negative 0.5, negative 0.1. We're getting closer and closer to 0, but from the left. And if you look at 1 minus cosine x over x, that's getting closer and closer to, and I know it's negative, right? But it's getting closer and closer to 0, okay? So these are both 0 equal to 0. That means whenever you see this limit, the limit as x approaches 0 of 1 minus cosine x over x, that's also 0. Okay, and let's do this last one. Let me slide this up a little bit. I gotta tilt my camera just a little bit so you guys can see it. Okay, so this table right here is describing the limit as x is approaching 0 from the right again of this e to the x minus 1 over x. Okay, x is getting closer and closer to 0 from the right. The e to the x minus 1 all over x is getting closer and closer to the value of 1. So this is equal to 1. This one right here, this is the limit as x approaches 0 from the left of e to the x minus 1 over x. And what are the y values doing? Or what is the value of e to the x minus 1 over x approaching? Well, it's also approaching 1. Okay, so that means, okay, this is not a proof, but what that means is the limit as x approaches 0 of e to the x minus 1 over x is also equal to 1. So we're going to use these, so we need to know what these values are, okay? And I'm going to use that. I'm going to show you next how we can use them. So these next two problems deal with trig functions, and we are not going to be able to do these algebraically, okay? Like, rationalize the numerator or cancel like factors or anything like that. And if we try to put zero in, we try to do direct substitution, okay, we get 0 over 0 again. But there's nothing algebraically we can do. But there's some stuff using trigonometry that we can do, okay? So this is equal to, okay, and I'm going to break this up, because if we try to do a direct substitution here, we're going to get 0 over 0, okay, because tan of 0 is 0, okay? And if we put 0 in here, we have 0 in the denominator. All right, so I'm going to break this up into, I'm going to basically, it's called decomposition. I'm going to break it up into factors, okay? So this is the limit as x approaches 0 of, I'm going to separate this, and I'm going to make this become 1 over x times tan x. So this is where we pick up trigonometry, that we need to remember some of the trigonometry and the trig identities that I showed you last spring when we were on distance learning, okay? So this is equivalent to the limit as x approaches 0 of 1 over x times, okay, so tan x can be rewritten, okay? This is one that's going to come up over and over and over again, okay? Some of the other trig identities won't come up as often, okay? But tan x can be rewritten as sine x over cosine x. Okay, so tan x is equivalent to sine x over cosine x, okay? Now, how does that help me? Okay, so I know that I can break this up even, and I can actually switch this numerator and this numerator. So I could rewrite this one as sine x over x, and this one 1 over cosine x. So this becomes the limit as x approaches 0 of sine x over x times 1 over cosine x. Okay, so this is the limit, and this is a product. I'm taking the limit of a product. What that means is, from the properties of limits, is I can take the limit of each one of these individually and get the answer and multiply those two answers together, and I'll have the answer for this, okay? So this is equivalent to the limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of 1 over cosine of x. Okay, so what we know from what we just talked about is we know this one, right? This turns out to be 1 times, and now we can do a direct substitution. So this is 1 over cosine of 0. Okay, so what is cosine of 0? Well, that's angle 0, right? Where's angle 0? Well, right here on the positive x-axis. Whenever we land on an axis, we always make r be 1. And because this is a circle with radius 1, this coordinate right here has to be 1 because we're going to the right. So the x-coordinate and the radius have to be the same length. And because we're going right, the x-coordinate has to be positive. And so the y-coordinate, I didn't go up and down at all. I just went to the right. So the y-coordinate's 0. And cosine is your x over your r, so this would be 1 over 1. So this ratio right here is 1 over 1, which is 1. So this becomes, I'm going to come off to the side here, this becomes 1 times 1 over 1. Well, that's just 1 times 1. So that means this limit is 1. And so this comes out to be 1. Now, if you try to do a direct substitution, you get 0 over 0, okay? All right, let's do the next example, and then we'll be done. All right, for this next problem, okay, it kind of looks like the one we just did, sine x over x, right? Except for it's not, because we have sine of 4x, okay? Now, for these, if you could get this to be a 4 right here, okay, then the angle argument for the sine and the denominator would match. So that's really our goal in this, okay? Because it turns out, and I can't go into details of why, it turns out that whenever you get this angle and this denominator to match, okay, when it's this particular one, okay, then you're going to be able to get it, okay? All right, so here we go. What can we do to this, okay? If we try to do 0, if we try to do direct substitution, the denominator will be 0, and then this will also be 0, okay? So what we can do is take the limit as x approaches 0 of sine of 4x over x. That's what we have, right? And we can change this by multiplying by 1. And the version of 1 that I want is 4 over 4. Okay? Now, why? Because now I can bring this 4 over here in with this x, and now I have the limit as x approaches 0 of sine of 4x over 4x times, okay, so that 4 is now with this x, right? So it's just times 4. Okay, now, because this is a product, okay, actually, I take that back. This, well, it is a product, okay, but it's a special product where you're multiplying by a number here, right? We can actually use the constant multiple rule, okay? So since we're taking the limit of something times a constant, we can bring that constant out, okay? So I'm gonna come off to the side here. So this is the same as 4 times, now if there was an x here, we couldn't do this, okay? It'd be 4 times the limit as x approaches 0 of sine of 4x over 4x. So again, it's not that these both have to be x, they have to be the same thing, okay? And so this turns out to be just like it would if it was sine x over x, okay? It would come out to be 1. So this turns out to be 4 times 1, and 4 times 1 is 4, okay? If you don't believe me, you could build a table and see that, and it would come out that it would get closer and closer and closer to this number 4, okay? All right, you guys, so that's a lot of algebraic techniques, a lot of review of algebra stuff that we learned last year, and hopefully, I know it's hard this year, but hopefully it comes back, okay? We're gonna be doing a lot of that, and that, like I said earlier, that's actually what makes calculus hard. It's easy to understand calculus. Calculus is actually really, really easy. It's all the algebra involved in actually trying to execute the calculus that makes it very, very difficult for a lot of people. Okay, so hang in there, guys. Okay, and that's it for today. Okay, and it's always weird to end these things. Okay, so I'm done. So let's just say it. Let's put it that way. Okay, take care, guys.